All right, in this lesson, we're going to learn how to apply the law of sine. We've seen the law of sines in math. This is how we're going to apply it to more of a statics problem. We have two forces acting in different directions, but they're converging at a point. Converging at a point right here. We know stuff about them. We know the magnitudes of F1 and F2. We also know the angle of F1 respect to the x-axis. With that, we could figure out what alpha is, and that's what I've done here in blue. So let's continue on finding out a couple of things. One thing is we want to find out, or the only thing in this case, we want to find out this theta here. Well, how do we do that? Well, we know one thing more than what's in the picture. We also know that the angle which makes the resultant of the two forces vertical. So if we add those two forces together, the result should be a vertical force. So with that, that's our hint to see what to come up with. And we can use what's called the law of sines. But first, let's draw a little bit of a picture of what this looks like. So we have this vertical line. I'm going to call this R. We have this force here, and that's the force at 2. Remember, we're saying that we're summing the vector forces of F2 and F1 to get R1. So we can say that the vector force R is equal to the vector force of 1 plus the vector force of 2. And again, we can do this in multiple ways. This may be the easiest. So what we want to do here is we know the alpha is equal to 20 in this case. We want to eventually find this theta. Can't do that directly yet, but what we can do is we can find this, and we're going to call this angle beta. Now the law of sines, if you're not familiar with the law of sines, or if you're to recap the familiarity with the law of sines, we can say that A, that's a distance, over the sine of alpha, which is the opposite of the length, is equal to B, which is another length, divided by the sine of beta. What that visually looks like is something that looks like this. So if I have A, this is alpha. If I have B, this here is beta. And you can see some of the relationship here between the two. So these are vectors, but what we can say is they also have magnitudes. So we're going to use the magnitudes of these the embeddedness of the already signs give the direction. So what we can say is F1, and we know F1, and we know F1 to be whatever it is. I think it's, well, let's take a look at what it is. F1 is 600 divided by the sine. In this case, the opposite from F1 is this beta here. Okay? And that is equal to F2 the sine of alpha. And that's how we can figure out what beta is. So let's figure that out. So we can rearrange this and we can say the sine of beta is equal to F1 divided by F2 the sine of alpha. We can also, further down the road, we can say that beta is equal to the arc sine of sine of, oops, sorry, not the sine of. We could say that f1 over f2, the sine of alpha. Oops, not beta. Let's get this right. The sine of alpha. And if we put in all of those numbers, we can say that beta is equal to 35.9 degrees. So we're not done yet, but what we do know is this. So if we do this and we redraw this diagram again, where this is the resultant, this here, and this here, we have F2, nope, I think that's F1, that's F1, F1, we have F2, we know that this is alpha, we know that this is beta, and we want to solve for theta. So we also know that if we add theta in this case, theta plus beta, because this is a 90-degree angle, and they have to equal 90 degrees. We can say that theta then is equal to 54.1 degrees. And that's how we can use law of sines in our statics problem to figure out and use vectors to figure out some of the angles in this problem. So that's it with the law of sines. To recap, we use the law of sines to figure out an angle. We can always use the law of sines. If we're given a couple angles, we can use it to find the magnitude and direction of other forces. So that's it for now, and I will see you next time.